room optimization. It's probably time to kind of raise some kind of misconception about what is room correction. Some people say and think if you have acoustic treatment, room correction is not relevant, or the other way around. In fact, they work together. I've seen some of you came with kind of sports cars. So if we try to make the analogy and consider a high-end loudspeaker as a sports car, installing a high-end loudspeaker in a living environment without any kind of acoustic treatment is more or less like driving a Ferrari in the middle of Milan when it's congested and with heavy traffic. You don't get the best out of your car, you're frustrated, and eventually your investment is not worthy. So treating a room is like moving your Ferrari from a urban environment to a racetrack. All of a sudden, you can go fast, you can enjoy, and, well, finally investing in a Ferrari makes sense. It's exactly the same with audio and acoustics. So where do we come into play? In fact, what loudspeaker room optimization, if we follow up on this kind of analogy, would be what we do on the engine, the gearbox, the tires. So we're here to fine-tune everything to further optimize the performance of the car given the environment. If you have, depending on the nature of the racetrack, if the racetrack has a lot of curves, or if it's very fast, flat, if it's raining, or if the track is completely dry, the mechanics will tune the cars very differently. So that's exactly what we're doing with room correction. So it's not here to fix a bad acoustic environment, even though it can do it effectively. It's here to further optimize the performance of the system, even in the ideal acoustic environment. So this microphone is kind of iconical and really represents Trinnov as a company, because it has 4 capsules, as you can see. Why do we use these 4 capsules? Well, first it gives us further information about the acoustic as we measure the system. And also, we are able to localize the loudspeaker in the room, just in a similar way as satellites are able to localize you with your cell phone. It's kind of triangulation. So using these 4 capsules and the time difference between those capsules, we can really precisely localize the loudspeaker in the room, plus minus 2 degrees in every direction, and very precisely in terms of distance. I can show it here. So that was the system as declared in terms of what loudspeaker do we have in the system and what channel do we want to play in. Now if I go to the more advanced interface, I can see what we got, what kind of information we got from the acoustic measurement using this microphone. So first you can see that we give a value for the RT60, which is one of the most dramatic information we can get in terms of acoustic environment. If it's too lively, if the RT60 is too long, it's not going to be suitable for a cinema. If it's too low, it's probably going to be too dry. So we get this information to start with. And then we have here in green the theoretical loudspeaker position. In an ideal world, that's where they would be. Of course, equal distance from the listening position. That's why they're represented in a circle. And then we also get the same information for the elevation plan. So where should be the left top middle loudspeaker in a Dolby Atmos system in terms of elevation, etc., etc. In blue and red, we get the loudspeaker position as we localized it during the acoustic measurements. So before, what I told you about loudspeaker placement and the challenge of finding the good compromise, indeed our recommendation, which is one speaker will play both Dolby Atmos and over 3D. As a consequence, of course, this loudspeaker placement will not be strictly compliant with the Dolby Atmos recommendation or the over 3D recommendation. It will be within their recommendations, but slightly compromised. With the technology that we have patented, which is called loudspeaker remapping, we effectively know the loudspeaker position in the room. We know the theoretical position of the loudspeaker depending on the format we're playing. And with processing, we're virtually reposition the sources where they should be, using all the loudspeaker in place. So that's how we kind of make it up for this slight lack of compliance with the strict recommendation of every format. So that's for loudspeaker positioning. So you got the graphical representation for the top view, elevation view, but you also get all the information in terms of distance, elevation, azimuth angle. And you also get a lot of information about what the system does, to time align the system, to level align the system. So as an example, if they're not equally distant from the loudspeaker position, which is quite obvious here, we have the left loudspeaker located at 9.72 meters. It gives you the kind of size of room we're talking about here. It's a very big room. Whereas the left surround obviously is closer to the listening position. As a result, to time align them, we obviously apply 13.15 millisecond delay to the left surround channel and only 0.94 millisecond to the left channel. So that's the kind of professional touch we have as opposed to other systems like DRAM, which is kind of a, push a button and hope it's going to do good things. Here we have complete information about what the system does, and of course we have a great amount of flexibility in terms of being able to correct this or further adjust. So that's for level alignment, delay alignment. If we now talk about proper acoustic correction, we can go to the graphs. And once again, in terms of what kind of acoustic information we give to our customers, we try to do more than other manufacturers. Well, first we come from a professional background. For this kind of project, given how much they cost and the expectation in terms of performance, we cannot afford to not give the required tools to the installer and calibrator to achieve the maximum results. So what we see here is before correction and after correction for left, right, left surround 1, left surround 2 loudspeakers. We could overlay all the 30 speakers, but it would make sense because you couldn't simply read it in an understandable way. So of course what we see here is not only we kind of linearize the response, but we also match the response between different loudspeakers. Because to create this immersiveness, and especially when you're talking about a room with that many speakers, what is critical is to get consistent amplitude, phase, and impulse responses from all speakers. Because when the sound comes to your ear, if it's inconsistent, first, when you have an object going around, the color will change, so it will be very disturbing, it will get you out of the movie. And if you get not only frequency response difference, but also time behavior difference, I can show you the phase as well. So in that case, I voluntarily chose to display speakers which were located in very different positions in the room. Let's say left, behind the screen, left surround on the side wall, and then you have right top front, left top rear, ceiling speakers. So not only they're located in different positions in a room, but maybe behind different fabrics, on the side wall or on the ceiling, so that will obviously affect the acoustic response and further complexify the way we have to optimize it. But more importantly, most of the time we will have different loudspeakers. For the front, which should be very big, powerful, possibly 3-way or 4-way loudspeakers, maybe 3-way or 2-way loudspeakers for the surround, maybe only 2-way, a little bit smaller loudspeaker for the ceiling speakers. As a result, different crossover implementation, different phase response, and that's even before you implement them in a room at different distances. So if we were leaving the system like this, that's the kind of phase inconsistency you would get. So all frequencies they are not really synchronized when they get to your ears. So we're trying to do as much as possible and as much as technically possible using processing. Of course, we don't feel it's relevant to optimize the phase response below a certain frequency, and there are some problems we cannot fix with electronics. That's typically reflections. So basically direct sound and early reflections coming out of phase to the measurement position. So this reflection is caused by a wall or a ceiling. So by electronic, of course, we cannot implement different absorbing material or push the wall back. So what's important here is the consistency we get across the phase response. That's true for home cinema, multiple speakers, but also in stereo. Aligning the phase response, optimizing the phase response gives you a better sound stage. If we look at the amplitude direct, that's also kind of interesting, because if I look at the amplitude and amplitude direct, I see these are very different. It's also the kind of information we provide that other solutions don't include, and that gives us critical information about the acoustic of the room. If you look at the amplitude only, that's what you would measure playing on peak noise and measuring with a real-time analysis spectrometer. It doesn't give you any information about the room. Eventually you understand that there is too much energy in the low frequency, not enough frequency at certain frequency, but you don't understand where it comes from. Is it coming from a bad crossover setup? Is it coming from a reflection? Is it the room mode? So what we do is, besides the amplitude response, we give what we call the amplitude direct. In fact, with our loudspeaker, with our acoustic analysis algorithm, we're able to, from the impulse response, extract the contribution of the room and only look at the response of direct sound and early reflection. And it shows us problems we wouldn't be able to see otherwise. Am I going too far in terms of technicality?
No, but we were noticing that you can do measurements of loudspeakers with this processor. You don't need any more dedicated measurements like Leo, and it even gives you more information. I mean, it's quite amazing.
Yes, it's very comprehensive. But in fact, no, of course, systems like Clio or dedicated measurement systems are even more flexible.
Yes, they're more flexible, but
different time frequency windowing.
Yeah, sure. But
here we're trying to focus on what matters and what is relevant as you calibrate the system. So typically this kind of information. So here, for instance, that's the left channel, 200 Hertz, massive deep. If we look back at the amplitude response, such as we would measure it, we don't see any problem. So if you only rely on that kind of measurement, you don't really understand what's going on. Here you obviously understand that there is a reflection, and you can check in the phase response, and you will see that it's consistent. We have a complete phase inversion at this frequency. So basically the reflected sound is out of phase, so we have a lack of energy. So that's, see, 200 Hertz, we have a complete phase rotation. And of course, as I said before, because it's a reflection due to proper acoustic problem, there's nothing we can do about it electronically. So you would need to do something in acoustic equipment, but at least you can see the information. All right, bass management. In this system, we have 3 subwoofers. Bass management, we designed this bass management system especially for this system and for the Altitude 32 because immersive sound needs more flexibility and more capability in terms of bass management. In studio, back in the days with 7.1, mixers were not invited and not encouraged to play full-range signals throughout the system, most likely only in the front. And loudspeakers, surround and backs, they were not full range. With Dolby Atmos, theoretically, based on the concept of the formats, we're supposed to have to be able to play full range material all around the system. So what the system allows you to do, well, first declare as many subwoofers as you want. The only limit is the number of outputs available. So if you have 20 speakers and 8 subwoofers, you need 28 outputs. So that's doable with a 32 channel limit. And it's not something exceptional. 8 subwoofers, we're doing this a lot, especially in the US, with companies really specialized in subwoofer placement and optimization. So they use probably 4 subwoofers for the FE alone, and then they use extra subwoofers for bass management. And dedicated subwoofers for the surround, for the ceiling, for the fronts. Possibly they will even built-in subwoofers in the ceiling. And in that case here we have 3 subwoofers in the system. We have all the speakers listed in this list. And for every combination of speaker sub, we can decide which subwoofer to use for the bass management of that channel. So for the left channel here, in that case, we're using only subwoofer 1 with 45 Hertz crossover frequency, that's for the fronts. And we boost the signal that is bass managed by 3.5 dB. You can set different crossover frequency for the high pass and the low pass, also different filter types and slopes. Might sound crazy and too flexible. Some installers, when they do complete custom systems, they choose their own drivers and they need that kind of flexibility to make sure that the off-axis response is okay, etc.
But if I buy a normal subwoofer which has this calibration with its microphone, would you suggest to use your system or always rely on
Our system.
No way.
Okay, so you just take the subwoofer, you
Yes.
put it there, and you...
You remove the setting.
Okay.
I did it because I like the machinery, but it is more precise and also the time alignment and everything. The better way is to disable the DSP if you can,
Yes.
because the DSP introduces a latency time that is a little bit more, but if you can do is, for me, it's better. My personal...
Yeah, that's how we do it also. Velodyne, just switch everything
Yes,
else.
yes.
No
I
filters.
was thinking of it.
Same.
So no, because the system will timeline subwoofer with the rest of the loudspeakers. Yeah, I mean
Okay.
it's more relevant because with the subwoofer built-in calibration, you don't consider the whole system. So it's
Yeah, sure.